Okay, welcome to EE222. We continue our lectures, and in yesterday's lecture, we looked at how we can build a more machine, right? So this is the good news is, insofar as examinations go, your more machine is the absolute last topic which we will be covering. Tomorrow's lecture, I will cover some. There will be obviously a quiz, right? Your final quiz, because we're not having a quiz now. So obviously we'll have a quiz tomorrow. There'll be your last quiz, and that's all the way in the afternoon at 5 o'clock. And we'll cover one more topic. I really wanted to show you practicals. My original intention has always been to show students the practical applications of these sorts of things. So there are two applications, two prominent ones, which are interesting. One is the traffic lights application, right? And there's a video on the Moodle shell of me explaining the traffic lights last year. So basically, that's just a state diagram going between red, green, and amber, right? Okay, so red, green, amber, red, green. So it's like a ring counter. It's going in the same direction, but the difference is in the timing, right? The difference is in the clocks. So you got to build clocks to do the counting. So count up till so green might be green for, let's say, 300 seconds. What is 300 seconds divided by 60 seconds? 5 minutes, yeah? So green might be staying at green for 300 seconds. So you have to point to itself for 300 seconds. So that's the sort of things which you've got to do. But otherwise, if you look at the overall state diagram, it's only three states: green, amber, and red. And it's going in the same direction. It doesn't change direction, right? Of course, that's just for a single traffic light. But the moment you have multiple traffic lights, then your system starts to go bigger. That's one system. The other system is that of a vending machine. Vending machine uses sequential logic, right? Because in vending machines, let me show you this. In vending machines, oh, I did not draw it over there. Okay. Well, let me just show you. In vending machines, the target is, let's say, if your can of Coke or can of soda comes out for $1, right? If your can of soda is priced at $1, why did this happen? Okay. Week 12, I should change that to week 12 and 13. Okay, if we go and look at the last problem. So if you look at it, it looks, let's say this is $1, $1. There are multiple pathways to get to $1, to $1. So let's say the vending machine only accepts 10 cents, 20 cents, and 50 cents, and $1. So it accepts 4 coins, right? Okay. So in order to go to $1, you can have 50 plus 20 plus 20 plus 10. So that means you would 50 plus 20 plus 20 plus 10, right, to get to $1. Or you may have directly to $1, just $1 coin, bang, straight, right? Or you may be going via 50 plus 50, so 2 states, 50 plus 50. And then obviously at every stage of the way, you've got to allocate for change, how much change there is. So that's why you'll have one final state, which is $1, but there might be other cases where you have $1.20, $1.10, and then obviously there's going to be drink to be dispatched, which is output of 1, and change as well. So a vending machine also uses state sequential logic, right? So those are two practical applications. Now another one which uses sequential logic, another system which uses sequential logic is, as I've said, the machine which deals with traffic lights. And there's a few others as well, but these are the two common ones which students usually engage on. So that will be tomorrow's lecture, and also we will have our quiz and our discussion on what is going to be in the final exam paper. All right. Okay, so what were we looking at when we left off yesterday? So we were looking at these two problems. You have to detect 111, right? And you either use, the question says use milli as well as more, all right? So let's draw the state diagram for milli. And today is week 13, lecture 2. So we're in the second last lecture of the semester. And the date is 22nd. Is that correct? 22nd? (22nd) 6002. All right. Now let's look at the state diagram for milli to detect. Okay, and I want to convey an important piece of information. All right, so I hope you have this from yesterday, this part here, right, A, B, C, right? So obviously our thing is going to be A, B, C, all right? Now it's milli machine. In a milli machine, do we show the output within the state? No, we don't, all right? Okay, now help me guys. Have a look at your yesterday's solution and try and assist me with getting this done. All right, so A stays at A. If input is 0, output remains 0, right? A goes to B, input is 0, input is 1, output is 0. So we are continuing the problem from yesterday, for those of you. So we are continuing the problem from here, all right? If I were to, let's see if I can, yeah, maybe you can see the entire thing this way. Yes, nice. All right, now, for B, if the input is 0, it goes to A, output is 0. B goes to A, if input is 0, output is 0. B goes to A, input is 0, output is 0. Now B goes to C, input is 1, output is 0. B goes to C, input is 1, output is 0. C goes to A, input is 0, output is 0. C stays at C, input is 1, output is 1. Okay, now let's go to the next state. So any errors over there, guys? Did I make any error? No. All right. Now let me finish the milli and then we move on to the more, right? Or should I do the more first? Okay, let's do the more first, right? So we say, so I'm doing everything in parallel. State diagram for more. Actually, it should be, I've got the wording wrong. It should be more state diagram to detect 111. Right? Okay. So let's have a look at more. In the more machine, you had A, B, C, right? Over here, maybe I should put down A and B same as, A and B would be same as milli. Yes, that's right. So I didn't draw it again. right? A and B will be the same as milli. That's good, right? Okay. Let's now draw the state diagram. Okay. Hey, you guys missed the quiz. You want to sit now? All right, okay. So look at it. You will have A, B, and C and D, right? A, B, C, D. So now we have to be careful when we draw it. A. My bubbles are slightly bigger. You know the reason why. Because you have A, B, C, D. And the purpose for D is to convey the output of 1. Right? The purpose of D is to convey the output of 1. All the rest are 0. So that's a Moore machine. So let's now finish it off. And over here, we're only going to do the loops. Right? So for A stays at A, right? Output is 0, input is 0. A stayed A, okay. All right. Input is 0, output is 0. So input is 0, output is 0. All right, that's how we know. Okay, now B. A goes to B. If input is 1, output will remain 0. If you look at it, there's only one place where there will be a 1, right? So remember I've said A and B same as milli, so that's why I'm referring to the milli machine, right? So for B, where was it? A goes to B if input is 1. A goes to B if input is 1. There we go. B goes back to A if input is 0. B goes back to A if input is 0. So guys, for those of you who just arrived, we're doing yesterday's problem. We're continuing it, and we are drawing the state diagram. So what we've already done is we've drawn the state diagram in the milli mode. We're now doing it in the Moore mode. All right, okay. Now, B goes to C if input is 1. B goes to C if input is 1. All right, we don't deal with this C. No, we don't deal with this C. We come here. This is the Moore C. C goes to A if input is 0. C goes to A if input is 0. And C goes to D if input is 1 and output is 1. C goes to D if input is 1 and output is 1. Right? Now, if input is 0, okay, D goes to A. Now, this is the tricky part over here. So, if you look at our logic diagram, there is a catch. There is an error over here. So, in our Moore machine, sorry, it's saying D goes back to D if input is 1. Yeah, D goes back to D because it detects. So where does this come from? Have a closer look. So D was the one, D, we had a D, let's come back right to the basics. We had 111 to be detected, right? 111 was to be detected. Now 111 is 3 bits. In order to detect 3 bits in sequence, you need 3 stages. So in milli, we have 3 states. In Moore, we need an additional state to output the 1, right? To output the 1, okay? So when we came over here, we said C points to D, right? And output is 1. So that is the reason why we have D output 1. Fair enough? Okay, now, what's the error in our last line, guys? What is the error in our last line? Yeah, this should be 1. This should be 1. Because if you look at it, you can still recycle from that and find an output of 1. Okay. So D points to D if input is 1. There we go. That's our state diagram for the more. So can you see with the milli and the more? Now, what's the next step? So we're going to complete the entire problem, right? Okay. What's the next step? The next step is the state transition table. For milli. All right. Now, what state diagram would you refer to in order to build the table? We would deal with the, which one? The milli, right? So over here, remember, this is one question in 2 parts. It's almost like there's 2 parts. Part A, you deal milli, part B with more. Eh? So I've done our analysis table with milli, our analysis table with more. That's only part of our own calculation. Then there was state diagram, milli state diagram, more state diagram. We've both done that. We're now going to the transition table, or some people call it the excitation table or the state table, right? Okay, state excitation table and so forth. All right, now, and this is where things get interesting for milli. So in more, okay, so what we do is we say, let's label our states. Let's now think of it, eh? Interesting. You can't just go and jump into the state table like that. Let's have a look at this. How many states, guys? 3 states. How many flip-flops do we need to entertain this? 2 flip-flops. Right? Okay. How do we find that? Right. Let's get this down. For milli, you had 3 states. 2 to the power of n should be greater than or equal to number of states where n is equals to number of flip-flop. So 2 to the power of n should be greater than or equal to 3. N will equal to what, guys? 2. So 2 flip-flops. Right? Let's choose. Did I mention which one we have to choose in the question? So let's say let's choose T. All right. Now, state assignment. So you have state, you have Q, QX, QY. I just want to give you something different, right? QX, QY. Right? It doesn't always have to be Q0, Q1, or QA, QB. Right? QX, QY. State A, B, C. It'll be 0, 0, 0, 1, 1, 0. Okay? All right, now, so what do we do? Our input is, okay, so we have X, you have QX. Okay, maybe I'll write it differently. QX, QY, input X. Sometimes people say QX star, QY star, Then you have T X Ty. Okay, Qx is current state. Let me put that different color. System input. Next state. Flip-flop inputs. System output. Yeah. So look at it. The way I've drawn it, what is different this time around? As compared to, by now you've matured in the game, right? It's just like in the beginning, when I used to draw Kano maps, I used to write down, okay, this is the window number. After a while, you don't need the window number. You should know, right? So what is different this time around? Okay, usually this X comes here, right? Now I've put it there. Doesn't matter. Doesn't matter. Why doesn't it matter? Well, simply because when we cycle through all the combinations, that X will be catered for, all the possible combinations, all right? Okay, so you can put it there, and sometimes it makes it easier to read your state diagram and transfer the information this way, all right? And look at this, next state I've put it in the middle. Usually next state used to come here. But see, this is a section. The double line means that's one section. This double line means this is another section. This is another section. This is another section. So 4 sections. Now, guys, the main point is, as far as input is concerned, the input section must come first. Input section must come first. Right? Input section must come first. Right? Okay. Now, what are we going to do? How many combinations will there be for this input section? 8. Why I like it in this way, you would realize, because then you can just go to a state, then you have 0, 1. From that one state, every state has either input 0 or output input 1, right? So you can refer to it to there. Okay, now let's go to our milli-state diagram. And over here, we can just make a small note that that's 0, 0, 0, 1, 1, 0. Guys, thinking of this, when you have a look over here at the state assignment, what comment can you make with regards to number of states and number of flip-flops? What's one particular information that you pick up? Yeah, one is unused. One is unused. One state is unused, right? So the good news is that when we do sequence detectors, unused states can be catered for. Only when we have a situation where you have unused states can be catered for using don't cares. But only when we do sequence generators, like problem 1 is sequence generator, problem 2 in your project is sequence detector, right? Sequence generators, then we've got to point to an unused state. Otherwise, it'll go and get stuck in a corner, and it won't be able to come out of that corner in a sequence generator if by fluke something happens. In sequence detectors, you're not outputting a thing. So as your input goes in, it will self-correct itself, right? If you build your thing on software, you'll see what I'm trying to inform you of. Okay, now, all right, let's populate this, eh? All right, 0, 0. It's here. Okay, maybe I can do it like this, right? 0, 0, input 0, output 0, right? Input 0, output 0 goes to, stays at A, eh? Stays at 0, 0. Okay. So 0, 0 stays at 0, 0. Input 0, output remains at 0. Yeah? Input 0, output remains at 0. Okay. Right now. 0, 0, input 1 goes to 0, 1. right? Output is 0. 0, 0, input is 1, goes to 0, 1, output is 0. See how it's so easy to translate. When you put x in this line, it becomes easy to translate. Now, 0, 1, see 0, 1 is the next one. So we now sent it over here. We've done and dusted this. 0, 1, input 0 goes to 0, 0, output 0. 0, 1, input 0 goes to 0, 0, output is 0. We know our sequence detector in this lane will only come to 1 once. There will only be 1, 1 in that particular Y lane. Right? Now, by the way, in your, oh no, not sequence detector. In your thing, you have two outputs. One output is, yeah, only one output. Yeah, one output, right? For sequence generator, prime number output. Yeah, and the other outputs are just the outputs which feed into your 7-segment decoder. Right? Okay. 0, where were we, guys? 0, 1, we have 0, okay. And what about 1? 1 will bring you to 1, 0. 1 will bring you to 1, 0. Output will be 0. Now 1, 0, input 0. 1, 0, input 0 goes to 0, 0. Right? And output is 0. 1, 0, if input is 1, it will stay at 1, 0. 1, 0, if input is 1, it will stay at 1, 0. Output will be 1. Yeah? Everyone in agreement with me? Right. What can you tell me about this one, guys? 1, 1. 1, 1 doesn't arise, doesn't show up. So you say, don't care. This is the catch. All right. Now, let's move. Let's populate this final table. Okay. What can you tell me, guys? What can you tell me about this thing? So we follow the same line. Make sure you do use different colors or something so that you don't confuse yourself. Like the way to do it is you take some different color pencils, right? And then QX and QX star, you color code it. Of course, it was easy in your project. You could use Excel. How many of you guys used Excel to draw up your table? Excel, very nice, I like it, right? How many of you went one step further and coded your Boolean algebra in Excel? Yeah, one guy? This table, yeah? How many of you were able to code your Boolean algebra? Code, I'll show you that. When I say code, maybe the word code people are, because you guys are engineers, you guys should know how to use code, right? Okay, 1, 0, 1, 0, right? And then 0, 1, 1, 1, 1. Let's say T gate, eh? Let's say this is Q, this is Q star. Obviously, what is D? If it was D, and if it was T, right? If it was D and T, let's say you had to do 2. So what would be your D input be? If it is D, right, it'll be the same as what? Q star, right? So all we do is we do that equals, you guys, did you guys do Excel in any of your courses? Okay, so that's fairly easy, right? Right? Okay, set done, right? D was fairly easy. What can you tell me about T, guys? T is what? XO. What? XO between Q and Q star, right? That's how I did. Right? So when I look at your solutions in your project, I didn't go and calculate for each and every student one by one. It's all Excel generated, right? I punched in the formula, but the Excel did all the execution for me, right? Okay, so that's how you do it, right? Especially when you guys list was, I believe, 32 long. Yeah, 32 long. Yeah, all right. 32 possible combinations. I mean, yeah. Okay, so what I'm trying to say over here is, as an engineer, you've got to use technology to your side. I know one or two students, they were using a mobile phone app to check their economaps. That's good, right? Okay, right? That's fine. But you've got all these other basic stuff. You don't need to download a special program or write some special code. It's all there. You know, it's all in Excel and all that. Okay, let's come here. So what I do is, this is my tip to you. Everything to do with X, you use, let's say, blue pen. QX, QX star, use blue pen. QY, QY star, TY, use black pen. And then if there's a third one, you use, let's say, pencil. Right? Okay, so you have it color-coded so you don't confuse yourself. Right? Color-coded so you can see things. All right, 0 XOR 0. What do you get? 0, 0. You see, you can also spread your fingers. 0, 1, 1, 0. What do you get? X. X. Right? Okay, okay, so these two lines are X anyway. Then you, okay. No, that's a 1. Somebody said 0. 1. There we go. That's how I track it. Okay? Use your fingers. If your fingers can't spread, spread something else. Okay. Okay. All right. Now, TX. QX, QY. All right, let's fill it up. T. 0, 0, 0, 0. Okay, just correct me if I'm wrong, eh? Y 0 triple 1. Just correct me if I'm wrong. If I make a mistake, then 00 X. Y all zeros. Any mistakes, guys? Because I usually make mistakes in my economaps. Okay, now, how are we going to do this? You can plot these two together. Plot those two together. This one can make a big loop over here. Can make a small loop over there. This one here can make this. So we can say Tx is equal to, what can you tell me, guys? It'll be x bar and Qx and x and Qy. Am I correct over there in the first one? Yeah, okay, second one. Ty will equal to Qy, yeah? Is that big one over there, Qy? Qy. Qy, or x and Qx bar. And what do you have for y? Y will equal to x and Qx, right? Okay, so that's how you do it, right? Now, we're almost out of time. Let's have a look at this one. I think by now you guys are starting to get the hang of how we draw your diagram. So once again, if we translate it to this, what can you tell me will be the difference? Let's first go to state assignment. Before we get to the state excitation table, state assignment, what's going to be the difference for the more? Milli is done and dusted. Eh? Milli, the next step is to draw the circuit diagram. Okay, so there will be a D, yeah, state D, and you can assign it 1, 1. Now, the catch is, somebody will say, hey, what if I assign this one as 1, 1, this one is 1, 0, this one is 0, 0, and this one is 0, 1. It'll still work. The machine will still work, right? Because of the consistency, it balances itself out. All right? Okay, now, what will be the difference in this table? The title, the header. You get the header right? That's why I always, in 2 of my quizzes, and that one question will not be coming tomorrow. Most of my quizzes, I had this question. Write down the header, right? The title, the header line, right? For your particular state excitation table. Tell me, what would be the header for the more table? Anything difference? No, no difference. Exactly same. Same header. What about this? How many combinations? Same, 8 combinations, right? Of course, what's going to be different inside the population over here? There'll be no x's, all right? You'll be using some real numbers, all right? Okay? Any questions, guys? So everything will be identical. And then, of course, your Carnot maps will follow. Same sort of Carnot maps, right? But no x's this time. Why did we get x's? Because there was an unused state. So that's what I wanted to show you. I wanted to show you how you handle the unused state. Right? Now, guys, I'm going to separate this. I don't know if you noticed it. If you come to your week 11, I don't know why it's labeled as counters. If you go to week 11 and 12, and then you scroll down, you know, you guys are all familiar with all of this now, all of that. In this particular note, I think it was taken out from somebody's textbook. They even have the transition. Transition means going from 0 to 1, what does it go to? But we just do it within the table, right? Flip-flop inputs, all that. Okay, you're all familiar with this. Okay, then you come to week 13. So what I'll do is I'll separate that week 13. And then you have the more, milli, and all that sort of thing. And then you have here. You have all our sequence detectors in here as well, all right? Okay? We have our sequence detectors over here as well. Milli with D flip-flop, same question but with milli, with JK flip-flop, you know, same question but with milli. I don't know what exactly the question was, because this note wasn't written by me, it's before me. What does it say? Does it say in the example? I think it's to detect. Yeah. Sequence of 3 or more ones in a row through serial input. Okay, so it's similar problem to what we've just done. So basically, you can have a look, guys, and there's a number of things over here. All right. Okay, so million more. So week 13 notes are there as well. All right. Okay, so that's it for today's lecture. We will meet you in tomorrow's lecture, and we will have our final quiz and your coursework. Your coursework, there's a couple of things. Your quiz number 4 mark will be ready by early next week. Your quiz number 5, because you're just doing it tomorrow, it'll be ready by mid next week. Your lab marks should be uploaded by this Friday. I've already got it. We're going to upload it very soon. Maybe tomorrow midday, in fact. I'll upload the lab marks. So you have a fair idea of where your standing is. Now, if you have missed any assessment item due to, let's say you were sick or something, obviously I expect that you would have had some kind of medical certificate, or if somebody was sick or there was a death in your family, then yeah, you should have advised me earlier on or something. I know 1 or 2 students did advise me, and we'll take that into account, all right? Yeah, let me know if there's any